A2, A3, A4. Okay. If it is 4 by 4 matrix is given, we are giving the notations for row wise A1, A2, A3, A4. Column wise also we have to give the same notations A1, A2, A3, A4. Okay, this is compulsory. So if it is A1 is assigned to A2, let us suppose, because we are giving the same notation. And here A1, we cannot get the A1 assigned to A1, A2 assigned to A2, A3 assigned to A3, A4 assigned to A4. Why? Because if it is A1 is assigned to A1, it means here starting point is A1 and ending point also A1. But in between this, it is the person does not visiting remaining intermediate branches. That is A2, A3, A4. So this kind of model problem is not an assignment model problem. So not an traveling salesman problem. So that's why in the question itself, they will give the A1 to A1. A1 perform the A1 job with maximum number of times. That is, they will give the simply hyphen or they will give the capital M. It means maximum time. Or some of the textbooks is giving infinitive. So A1 can perform A1 job at infinitive stage. Similarly, A2 can perform A2 job infinitive stage. A3 can perform A3 job at infinitive. A4, A4 like that. So they will give the in diagonal elements. Simply we can say the principal diagonal elements must be infinitives. In that kind of model problems only we can perform the Hungarian assignment method process. Finally, we can get the whether it is a traveling salesman problem or not. Okay, I will show with one examples here. I will share the screen. 1 minute. Screen share just I will share the screen. Wait for a minute. I will explain traveling salesman problem with one example. Just wait 1 minute. This document is where it is. One minute. Just wait for 1 minute. Yes. Is it a screen is visible? Yes. Is it screen is visible? Right. See here. Traveling salesman problems. Okay. This is known as, in our textbook we have title with routing problems. Okay. In our textbook, the title name of this traveling salesman problem is given routing problems. Yes, I will repeat the once again that there is a definitions here. The traveling salesman problem is a very similar to the assignment model problem, except that what is the main difference? The notations must be row wise and column wise must be similar. So except that in the former there is an additional restrictions that a salesman who starts from his home city and visit each city only once and return to his home city. So that is, if the salesman starts from city A and he has to visit each remaining cities at only once, and he has to come back to his home city, that is city A. So where he was started, and again he will going to come back in that station only. Which uh, which route would you advise him to take so that total distance should be traveled by him? That should be minimum quantity. So in this principle, we have to give the suggestion to that person which point is the suitable for starting, and from that point to he has to visit all his intermediate branches at only once. After visiting all branches, again he will come back into the his home city with total traveling cost must be least. That kind of model problems is known as routing problems or traveling salesman problem. The best example for traveling salesman problem is a postman duty. Okay, a postman duty. What is a postman duty? Just just consider how a fashion delivers the parcel. This is the complete example of that postman duty. This is okay. I don't want to repeat once again this one. Just I will go through the next slide. See here. See here. Yes. So there are two different types of traveling salesman problems. That is routing problems. One is cyclic problem. That is symmetrical problem. What is cyclic problem? Yes, the person will start at any position and he will visit all that intermediate branches at only once. After visiting all branches, he will come back into the his home place where he was started. That kind of model problems are known as symmetrical problems or cyclic problems. These type of cyclic problems can be solved by Hungarian assignment method. Next, acyclic problem. Acyclic problem is, what is the definition? Is the person can start at any one of the station and he will visit all his intermediate branches at only once, and after visiting all branches they will stay at the last branch only. He never come back into the his home position. That kind of problems are known as asymmetrical problems or acyclic problems. These kind of acyclic problems can be solved by dynamic programming method. Later we will discuss these methods. Okay. Next year I will give the one example here. So here uh, solve the following assignment model problem. So has to find the total traveling distance. Okay. So here I'm taking 5 by 5 matrix, rows A1, A2, A3, A4, A5, and columns A1, A2, A3, A4, A5. Okay. I'm giving the notation similar. See, just compare this problem with your previous examples. So previous example there I have taken, yesterday I explained the problem. So that is I given the notation A1, A2, A3, A4, A5, and row column wise I given another notation from 1, 2, 3, 4, 5. And some A, B, C, D, E, F, G, H, like that. But here, what is the first condition? The notations must be similar, row wise similar, column wise similar, and apart from that, one more condition. And what is that? See, principal diagonal elements are unrestricted. Yes, is it visible? A1 to A1, that is infinitive. A2 to A2, that is infinitive. A3 to A3, infinitive. A4 to A4, infinitive. Similarly, A5 to A5 also, it is infinitive. It means A1 can perform A1 job, but it will take maximum time. That's why I'm putting that is infinitive. A2 is also performing A2 job at a maximum number of times. That's why I'm putting that is infinitive time. Similarly, A3, A4, A5 also. So principal diagonal elements are strictly unrestricted. For this problem, if you apply uh, what do you call it? That is the Hungarian assignment method. Row subtraction, column subtraction. I'll show you 1 minute. So if you apply these problems here, first 1 minute. ఒక 10 నిమిషం. Yes, I will note the point, the problem. Just wait. What is the matrix? Infinitive 2, 5, 7, 1, 6, infinitive 3, 8, 2, 8, 7, infinitive 4, 7, 12, 4, 6, infinitive 5, 1, 3, 2, 8, infinitive. Okay. Here, I'll solve these problems here. Yes. So I'm taking this is a 5 by 5 matrix. Mm. Yes, is it visible? Yes. Mm. So this is traveling salesman problem. Traveling traveling salesman problem. So this is 5 by 5 matrix. Of course, this is a balanced assignment model problem. Okay. So first give the notations, similar notations by row wise, column wise. A1, A2, A3, A4, A5. Okay. Next, here, column wise also we have to give the same notations. A1, A2, this is A3, A4, A5. So if I say this is traveling salesman problem means we have to start, let us suppose the final assignment will be like this. If A1 is here, starting A1, then A1 is assigned to, let us suppose, some A3. A3 is assigned to some A5. A5 is assigned to A2. A2 is assigned to A4. Finally, A4 is assigned to again A1. So the starting and ending assignments must be coincide. And in between these two, all intermediate branches will be visited at only once. Then these kind of model problems we are calling it is a traveling salesman problem. Suppose if it is the solution is like this: A1 is assigned to A2, A2 is assigned to A3, A3 assigned to some A1. Let us suppose. So here also starting and ending points are coincident, but in between these two, all intermediate branches are not visiting. Only A2 visited, A3 visited, but A4, A5 are not visited. So this is not assignment model problem. For these kind of model problems, we have to arrange by selecting instead of 0, next immediate least element, we have to take the assignment procedure. Okay, I will show this problem with an examples here. So this is, okay, we have totally 5 by 5 matrix. 5 rows, 5 columns. So it is balance assignment problem. So first, row subtraction. What is the procedure? This is question. What is the procedure? Step 1 is row subtraction. Row subtraction, we are going to take least element and subtract that least element by row wise and subtract in that corresponding row only. In first row, this is infinitive, means maximum. 2, 5, 7, 1. 1 is the least. So we have to subtract 1 from remaining all elements. Infinitive minus 1. So infinitive minus something means again it is, we'll get infinitive only. Infinitive. 2 minus 1, 1. 5 minus 1, 4. 7 minus 1, 6, and this is 1 minus 1, 0. Similarly, in second row also. In second row, which is the least element? 6, infinity 3, 2. 2 is the least element. So 6 minus 2, 4. Infinity minus 2. Again, it is infinity only. 3 minus 2, it is 1. 8 minus 2, it is 6. 2 minus 2, 0. Next, in third row, 4 is the least element. So subtract that 4 from remaining elements. 8 minus 4, 4. 7 minus 4, 3. Infinity minus 4, 4 minus 4, 7 minus 4. Right? Similarly, in fourth row, 12, 4, 6, 5 means 4 is the least element. So 12 minus 4, this is 8. 4 minus 4, 0. 6 minus 4, 2. Infinity minus 4, again it is infinity. 5 minus 4, 1. And last row, 1 is the least again. So subtract 1 from this. 1 minus 1, 0. 3 minus 1, 2. 2 minus 1, 8 minus 1, infinity minus 1. Okay. This is row subtraction. So notations are A1, A2, A3, A4, A5. Similarly, here also A1 column wise, A2, A3, A4, A5. Next, what is next step? Yes, what about our next step? Yes, it is column wise subtraction. Okay. So I will do this. This is step 1, step 2. This is step 1, this is step 2. Column subtraction. So column subtraction means in each and every individual column, we have to select the least element and subtract that element from remaining all elements from in that corresponding column only. In first column, 0 is the least. So if 0 minus something means we will get the same column here. Infinity minus 0, 4 minus 0, 4 minus 0, 8 minus 0, 0 minus 0. Next, second column also we have least element is 0. So if you subtract 0 from remaining elements, we will get the same column elements. 1, infinity, 3, 0, 2. Okay. In third columns here. Third column we have 1 is the least element. Okay. We have to subtract this one from remaining all elements in that corresponding column elements only. 4 minus 1, 3. 1 minus 1, 0. Infinity minus 1, 0. 2 minus 1, 1. 1 minus 1, 0. Next, similarly here, next fourth row, fourth column we have 0 is the least. So we'll get the same column elements. 6 minus 0, 6 minus 0, 0 minus 0, infinity minus 0, 7 minus 0. Next, fifth column, again it having 0 is the least. So if you subtract 0 from remaining elements, it shows same column. 0, 0, 3, 1, infinity. So these are the basic steps. Row subtraction, column subtraction. After this, we have to take the assignment procedure. Okay. I will do that process here. So this is 7. So first take the notations by row wise and column wise must be same. This is A1, A2, A3, A4, A5. This is A1, A2, A3, A4, A5. Okay. See here. First, in first row, where now coming to the assignment procedure. In first row here we have 0. So I'll indicate assignment here. Next, see, is there any extra zeros by row wise, column wise? We have to strike out them. Row wise, there is no extra zeros. By column wise, we have one extra zero. So I'm going to strike out this one. Next, second row, here we have 1 0. Okay, this one assignment done. And see, is there an extra zeros row wise? Yes, 1 0 is extra, but already it is cancelled. By column wise, have one extra zero here, that should be cancelled. Next, in third row, 4, 3, infinity to 0 means yes, here we have 1, 0. Take assignment in that corresponding row. And it is there an extra zeros by row wise or column wise? Row wise there is no zeros. Column wise also there is no zeros. Next, fourth row. Fourth row is here we have 0. So I'll going to take assignment here and strike out extra zeros by row wise, column wise. There is no extra zeros by row wise. There is no extra zeros by column wise. Next, similarly fourth row, last fifth row. Yes, we have one more zero here. So extra zeros, there is no row, there is one extra zero in row wise, but already it is cancelled. But column wise, there is no extra zeros. Now check out. In each and every individual row, the assignment is done. In first row, here we have assignment. Second row here, third row here, fourth row here, fifth row here. So coming to the optimal assignment. So A1 is assigned to A5 because the notations are A5. Next, A5, see, A5 is assigned to, so we have to write this is in sequence order, not A1 assigned to A2 assigned to, don't write down like this. A1 is assigned to, here, yesterday I explained the problem like this. A1 is assigned to so and so, A2 assigned to so and so, A3 assigned to so and so, A4 assigned to so and so, and A5 assigned to so and so. Do not write like this because here the notations are sequence notations are here same, here also same. So we have to take the assignment. A1 is assigned to A5. Next, see what about A5? A5 is assigned to A1. See here. Here, A1 and A1 are coincide. Okay. So it is cyclic problem. Is it clear? A1 is starting point is A1, again ending point is A1. But in between these A1, all intermediate branches, listen carefully. In between these A1 and A1, all intermediate branches are not visiting because here A2 missing, A3 missing, A4 missing. Only A5 is visiting. It means it is cyclic problem or it is assignment is exist. In each row, every row, assignment is exist. Means for this assignment model problem, the optimal assignment is exist, but it is not and transportation model problem. Why? Because in between A1 and A1, all intermediate branches are not visiting. Hence, it is only just assignment model problem, but not a traveling salesman problem. Because A2, A3, A4 are missing. So we have to adjust that into the by taking next immediate least element. So assignment exists, but it is not a traveling salesman problem. For converting this into traveling salesman problem, just I will take this problem into some general modification. See here. What about this here? Yes, I will do same that table. I will take the same table once again. Infinitive 1, 3, 6, 0, 4, infinitive 0, 6, 0, 4, 3, infinitive 0, 3, 8, 0, 1, infinitive 1, 0, 2, 0, A1, A2, A3, A4, A5. And this is also same notation, A1, A2, A3, A4, A5. Now, this is assignment is done, but it is not a traveling salesman problem. So we have to adjust this as a assignment model problem. So first, here in previous problem, there I have taken 0 is the assignment. With the help of 0, I did all assignments in each and every individual row. But if you do like this, the assignment is existing, but it is not comes under the traveling salesman problem. So we have to make them this into traveling salesman problem by taking instead of 0 element in row wise, instead of 0 least element, we have to choose next immediate least element in first row only here. In first row, with the 0 is the least element. So 0 is the assignment. If you take this one, we got the assignment is exist. Optimal assignment is exist. But it is not traveling salesman problem. So for converting this into traveling salesman problem, I am choosing instead of 0, yes here, instead of 0, select next immediate least element in that row. So here infinity 3, 1, 3, 6, 0 is there. 0 is the least. Next, instead of 0, next immediate least element is 1. So I am starting with these box as an assignment, because if you choose 0, with the help of 0, it is not getting the traveling salesman problem. That's why I'm selecting instead of 0, I'm selecting the 1. And next, one, the assignment is done. Remaining procedure is same. We have to do the same process. So here assignment is done. And strike out. Is there any extra zeros by row wise and column wise in that corresponding one? So here this is first row. Extra zero here we have. I'm going to cancel this one. And column wise here we have one extra zero. I'm going to cancel this one. Next, coming to the second row. Second row again. So do same zero only. Do not take next immediately element, because in the first row I'm taking instead of 0, I'm taking 1. With the help of 1, let us check out whether it is traveling salesman is existing or not. If it is not exist, then go further. In second row also, next immediate list element. Okay, first here. In second row, first we have to check out with zeros only. Okay, so in first row, here we have 2 zeros. So I'm going to take this one, this 0. Okay, right? So this is extra zeros cancelled by row wise and extra zeros cancelled by column wise. Right? Next, third row. Here, third row we have this is 0 is here. Extra zeros. There is no extra zeros by row wise. There is no extra zeros by column wise. And fourth row here. Fourth row, we have only one single 0. But already it is cancelled. So there is no zeros. Okay. So if it is zeros are not given, means assignment is not done in this. So, but already, what is our problem? Already the optimal solution is existing. The optimal solution is existing. Each and every individual row, I got assignment. Just I am making this as a traveling salesman problem. So do not go further again that tick mark or again that straight line procedure. Okay, just we have to rearrange this problem into assignment into traveling salesman problem. Okay, so here zeros are cancelled. Okay, all zeros are eliminated. But instead of 0, what is next immediate list element here? Yes, 1 is there. So 1 is present here. But if you choose this one, already in this here, in this, we have in fourth row, we have 2 ones. Okay, either you can choose this one or this one. But if you choose this one, yes, is it clear? So if you out of these two ones, if you choose this one, if you choose this one, it shows that already these A3 person, if you assume this is persons and this is jobs, already this A3 job is assigned to A2 person. Okay, do not assign same job to other person. So leave it this. So other than this one, in this fourth row again we have one more one. So I'm going to choose this. Okay, of course I'm telling once again here. Of course zeros are not present. Do not go for the tick mark process or straight line process. Why? Because already for this problem assignment is done. Assignment is done each and every row. But I'm converting this problem as into a traveling salesman problem by taking some rearrangement, by choosing next immediate list element. Okay, so that's why I'm not going to take the tick mark process. So even the zeros are not there in fourth row, but next immediate list element is there. 2 ones are there. So instead of this, I'm going to choose this one. So this is the assignment in fourth row. See, extra zeros are cancelled. Next, last row. Yes, here we have one more 1 0 here. So assignment is here and extra zero is cancelled. Row wise already it is cancelled. Column wise there is no zeros. Now check out. First row we have one assignment. Second row we have one assignment. Third row also we have. Fourth row also here we have. And in fifth row also we have assignment. So now again write the optimal assignment quantity. Optimal assignment. So what is optimal assignment? Yes, write down like this. A1 is assigned to A2. Next, A2 is assigned to A3. See here, A2 is assigned to A3. A3 is assigned to A4. Next, A4 is assigned to A5. Again, A5 is assigned to A1. It means the first and last are coincide. Okay, where the person is started and that same branch is ending also. In between these two, let us check out all intermediate branches are present or not. A2 is present, A3 is present, A4, A5. Yes, all four intermediate branches are present. It means the meaning of this is yes, it is optimal solution exists and it is an example of traveling salesman problem. Traveling salesman problem. So why I'm calling this as a traveling salesman problem? Because the starting and ending points are coincide and in between these two, all intermediate branches are visited at only once. Therefore, it is an example of traveling salesman problem. Therefore, the final time duration will be, what about time duration? You can come to the original question. What is our original question? Yes, here. This is original table. So A1 is assigned to A1 is assigned to A2. That is just indicate here circles like this A2 and A2 is assigned to A3 and A3 is assigned to A4. A4 is assigned to A5 and again A5 is assigned to A1. Therefore, the total time will be yes, 2 plus 3 plus 4 plus 5 plus 1. So what is total time? So it is 1 plus 2 plus 3 plus 4. Sum of the first five natural numbers means 15. So 15 hours. So within 15 hours, these entire 4 persons can be performed. These are 5 persons can be performed. These 5 jobs within a 15 hours period of duration. Okay, this is traveling salesman problem. So just is like this. Then it is traveling salesman problem. In this year, before adjusting this, here we got the chain will be like this. So it is not assignment problem. Sorry, it is not traveling salesman problem. It is just only assignment model problem only. So by taking some rearrangements after after existing optimal solution, just I am taking some rearrangements so that I can adjust it all the branches to like this A1 to A2 chain rule. So A1 to A2, A2 to A3 like this. Okay? And one more thing, it is not compulsory to choose like this in sequence order. First A2, next A3, next A4. It is not like that. If it is for this problem, I got like this. If it is in zigzag order also, but all intermediate branches must be visiting. Then only A1 and A1 will be coins. This kind of model problems are known as traveling salesman problems. Okay. Is it clear? Traveling salesman problem. So what I'm saying, the, the main definition for traveling salesman problem is the person will start from anywhere, so and so branch. He will start at so and so branch and he will visit all his intermediate branches at only once. After visiting all branches, again he will come back into the starting position where he was started. That kind of model problems are known as traveling salesman problems. Okay. Next. Okay. This is assignment model problems if completed. Next, I'm going to start the uh, game theory problems. Game theory. Okay. So this is one of the very easiest topic, game theory or theory of games. And in this year, we have totally 3 methods. One is, so solving the game theory problems, we have total 3 methods. One is dominance principle, graphical method, and simplex method. That is, already you studied simplex method in unit 1, LPP problems, linear program problems. But in our syllabus, we have only 2 methods. We don't have any graphical method. We have only dominance principle as well as linear programming problem method. First, coming to the what is the meaning of game theory, or what is the meaning of this theory of games. See here, I will give the general examples here. Suppose whenever there is a competition between two persons, whenever there is a competition between two persons, then we have to decide which is the best. So it's a person A, person A. Suppose there are two shops, shop A, shop B, and shop A is giving on his sales is giving so and so percentage discount, and shop B also is giving so and so percent discount. Now the customer will decide which is the best. So in that situation, these game theory will play a major role. So whenever there is a competition in business situations, we have to decide which is the best. In that situation, the decision making will play a major role. That kind of model problems can be solved by these game theory concepts. Okay. So in game theories here, first come to the terminology in game theory. Around we have 8 to 10 definitions. I will discuss one by one here. First, definition one. Player. The meaning of player. What is the meaning of player? General definition. The person who has to participate in a game. Player means the person who is going to participate in a game is known as player. In game theory, we have only two players. In game theory, we have only two players. Sir, just I will take the 5 minutes, sir. Just I will conclude my class within 5 minutes, okay? Right. See here. So game theory means player means player. The person who has to participate in a game is known as player. In game theory problems, there will be only two players, player A, player B. In each and every individual game in this game theory or problem in game, we are going to take only two persons. One is player A, one is player B. Okay. And next coming to the payoff matrix. As this is one of the most important payoff matrix. I will show it. Okay. Payoff matrix. Yes, see here. Payoff matrix. Payoff matrix. As coming to the payoff matrix means, see here, in every game there will be problem like this. This is player A information. Row wise, I am going to take player A information, and I am going to take column wise with player B information. Okay. Let us suppose this is strategies or plans. P1, P2, P3, and this is some Q1, Q2, Q3, or Q4, whatever it may be. Okay. So in this, suppose if the elements are like this 1, 2, 3, 4, 5, 0, -2, 5. So I'm taking P3, P4, and Q4 also. 5 minus 1, 2, 3, 4. Let us take whatever it may be, 0, 1. Okay. In this here, in this matrix, row information indicates player A information, or the row values indicates player A information, and the B column values indicates player B information. Okay. And if any one of the positive number is given, if any one of the positive number is given, here +1, +2, +3, 4. Positive numbers indicates the meaning of that positive number is it is the profit amount of player A. Yes, listen carefully. Positive numbers indicates and loss amount of player B. So it means here one is given. The meaning of this one is yes, one shows that it is a +1. So if you apply this strategy 1, player A will get 1 rupee profit amount and player B will lose 1 amount. So positive indicates player A profit amount, player B loss amount. If it is negative is given, let us suppose this is -2. -2 indicates it is profit amount of player B, loss amount of player A. Let's listen carefully. Negative elements indicate it is profit amount of player B, loss amount of player A. It means if you apply this strategy, P3 and Q1, if you apply the Q1 strategy, then player B will get 2 rupees profit amount and player A will lose 2 rupees loss. Okay. So positive indicates profit of player A, loss of player B. If it is negative amount, it indicates profit of player B, loss amount of player A. Yes, some of the values zeros are there. Zero indicates no loss, no gain to no loss and no gain or no profit to both players. Is it clear? So if zero indicates no loss, no profit to both players. So this is this entire structure. This entire structure is known as payoff matrix. Okay. So what is the meaning of payoff matrix? If positive values are given in that matrix, that positive indicates profit amount of player A, loss amount of player B. If it is negative values are given, it indicates loss amount of player A, profit amount of player B. And if it is zeros indicates what? Yes, no loss, no profit to both the players. Okay.